After discussing the solubility of solids in liquids, now we are going to discuss about the solubility of gases in liquids. We must have observed in our daily life that the water bodies around us are having the aquatic life. Now everybody knows that for aquatic life to sustain, they need to have the oxygen. So some amount of aerial oxygen is getting dissolved in those water bodies, that's for sure. So we need to understand that there is a certain capability of the gases to form a solution when it combines with the liquids. That means here liquids are acting as a solvent and the gases are acting as the solutes. So how do we define the solubility of gases in liquids? Solubility of the gases in liquids can be defined as the amount of the gas. Obviously, amount of the gas normally is calculated in STP that can be dissolved in a fixed volume of liquid at a given temperature is to form a saturated solution is known as the solubility of gases in liquids. Now let us see the factors on which the solubility of gases in liquid depends upon. There are basically four factors. One is the nature of the solute, that is gas. Next is the nature of the solvent, which is liquid. Then the temperature of the solution and the pressure. Now let us see one by one how these factors are going to affect. Among the factors, we are now going to discuss about the nature of the gas and the solvent. Gas means here we are trying to say the solutes, right? Now, you see these gases that I have written, that is nitrogen, oxygen and helium, these are very less soluble in water. So it is their nature that they are not likely to get dissolved in water. Whereas you see these gases in water, their dissolution is much better. But here it is way less. So here it is a better soluble and here these are less soluble. One of the reason behind this is that ammonia, sulfur dioxide, HCl, they can react and they can interact in a better way with the water. So we can say that the gases which are having the capability to react or to interact with the water or the solvent, whichever solvent it is, will be better soluble. Now let us see the nature of the solvent. See, depending on the nature of the solvent also the solubility depends. We have chosen two different solvents over here. One is ethyl alcohol, another is water. Now if we see carbon dioxide, if we see oxygen, and if we see suppose nitrogen, these are better soluble in ethyl alcohol but not so much in water. Whereas in water we can see that ammonia, H2S, these are much better soluble in water. And if we put the same gases in the ethyl alcohol, the solubility is very less. So here we can see both the aspects. In one side we can see some of the gases are very less soluble in water, where some of the other gases are very finely get soluble in water. Same is applied for the solvent also. Some of the solvents like some of the gases like carbon dioxide, oxygen, nitrogen easily soluble in ethyl alcohol, but the same gases are less soluble in water. So it depends on the nature of the solvent. Whereas ammonia, H2S, they are better soluble in water compared to the ethyl alcohol. So solvent also decides how much will be the solubility and what will be the solubility. So in the first point we have discussed about the nature of the solute and solvent. Next is the effect of temperature. So here we can see, if we write down in this case the effect of temperature means we can say that solubility of a gas, this will decrease. It will decrease with increase in temperature. This is normally what that is what happens. What could be the reason? The reason is this one actually. If we take a gas and if we take the solvent and if it forms a solution, it always is an exothermic process. That means it gives rise to heat. So it is exothermic. So of course, according to Le Chatelier principle, heat is being generated on the right hand side. That means if we are putting heat over here on the left hand side, the reaction is not going to proceed on the right hand side. Means if you are increasing the temperature or the heat on the left hand side, the reaction will not go to the right hand side because it does not minimize the effect of the change. So that is why while increasing the temperature, what happens is that solution, this from right hand side, the reaction proceeds to the left hand side. That means already in the right hand side the heat is being generated in this process. So if we are increasing the heat on the left hand side, the reaction rather proceeds from right to left. That means gases and the solvents are getting separated out. That means the solubility decreases. Let us see the effect of pressure. In case of effect of pressure, we have observed that if pressure is increased, then the solubility of gases in liquids also increases. To understand this, I have drawn two diagram already. Here we can see this is the water body. This is the water part. And some amount of pressure is generated by keeping a weight. Here the pressure is more because I have kept more amount of weight over here. And this is a piston. So in this region that you can see, and in this region I am talking about, the water body is not there, gases are present. So suppose any gas, these are the gas molecules which I have drawn with the help of this red color. So the gas molecules which are present over here will be present over here as well. So the gas molecules are present here. Here, see the amount of gas molecule that is present. Since the volume is less, but the molecules, the number of the molecules will not go down. Let us draw 2-3 more molecules over here. So here, let us draw the similar numbers. Since the space is less, you can observe number of molecules which is directly interacting with the surface of the liquid in both the cases. On the right hand side, it is clearly more. So since the gas molecules moves around, they moves around in the vacant space, and the chances of the gas molecules to strike on the surface of the liquid, here it is much more. So since on the right hand side, because of the less volume, over here in the vacant space, the chances of the gas molecules to strike on the surface of the liquid is more. That is why the chances of getting soluble will also be more because of the higher interaction. So that is why we can say that in this case the solubility will be more soluble, and here it is less. So here you can see by increasing more pressure, the solubility increases. So through a small diagram, I have tried to make it clear that if the pressure is more, the solubility of the gases in a fixed volume of liquid will be more. Regarding the solubility of gases and liquids, William Henry has given a relationship which is also known as Henry's law. So the law goes like this, that for a fixed volume of liquid, the amount of gas that is soluble at a constant temperature depends on the applied pressure in equilibrium with the solution. At constant temperature, we can say mass of the gas dissolved in the unit volume of solvent, that is liquid, is proportional to the applied pressure. So we can say M is equal to K into P, where K depends on the nature of the gas, and obviously it is the proportionality constant. So this is one of the way to express the Henry's law. Another scientist, Dalton, at the same time has independently discovered that the mole fraction of a gas in the solution is proportional to the partial pressure of the gas over the solution. That means Dalton was trying to say that the mole fraction, which is small x of course, is proportional to the partial pressure, which is small p, in that solution. So we can write x is equal to k dash, just to keep a different constant because we have already written k, into small p. Now if you want to write this one, the p is the partial pressure. Now if you want to write p, so we should be writing 1 by k dash into x. So we can further write that p is equal to kh into x. That means we are basically writing this part as kh. Now this is known as Henry's constant. So from this equation, the Henry's law can be alternatively stated as the partial pressure of a gas in the vapor phase is directly proportional to the mole fraction of the gas in the solution. So you can see the partial pressure, small p rather, the partial pressure of the gas is directly proportional to the mole fraction, which is nothing but the Dalton's law. And so we can say that Dalton's law and Henry's law is almost similar to each other. So Henry's law can be alternatively stated with the help of this Dalton's law. There are a few limitations of this Henry's law as well. There are 4 limitations basically. It is observed that this Henry's law is only valid when the pressure is low, when the temperature is not too low, means at higher temperature it will not be valid. Gas is not highly soluble, and the gas neither reacts chemically with the solvent. It should not be dissociating or associating in the solvent. So these are the 4 factors then which should be kept in mind if we are talking about the validity of Henry's law. We must have experienced in our daily life that if suppose we take a cold drink bottle, if we take, we must have observed that the moment that we open its cap, what happens? Some of the gas used to come out. It is the dissolved carbon dioxide which was there present within it. Now the question is obvious, why does it comes out suddenly? Because it was kept dissolved in an excess pressure within it, and when the pressure is removed, it is coming out. So that is what we have discussed till now, that when the pressure is high, the solubility of the gases within a given amount of liquid will be higher. And when the pressure is lifted, that we have seen in the cold drinks, that the gas will eventually come out. Means the solubility of the gases will be less and it will come out of the solution. Solve one problem related to Henry's law to understand the law in a better way. Students, you can rewind this video to understand the problem because I am reading it out, I am not writing it down. So the problem goes like this. The Henry's law constant for oxygen dissolved in water. So here we are talking about oxygen dissolved in water is 4.34 into 10 to the power 4 atm at 25 degrees Celsius. And here it is also given that the partial pressure of oxygen is 0.2 atm. So the partial pressure of oxygen is 0.2 atm. Now under atmospheric conditions, the question is calculate the concentration in moles per liter. So we have to calculate the concentration in moles per liter of dissolved oxygen in water in equilibrium with air at 25 degrees Celsius. So again I would like to repeat the question. The Henry's law constant for oxygen dissolved in water is 4.34 into 10 to the power 4 atm at 25 degrees Celsius. If the pressure of the oxygen in air is 0.2 atm, under atmospheric conditions, calculate the concentrations in moles per liter of dissolved oxygen in water in equilibrium with air at 25 degrees Celsius. Now let us see what Henry's law suggests. So according to Henry's law, it is P is equal to kh into x. Now here already Henry's law constant is given as 4.34 into 10 to the power 4 atm. So, and also this one is also given, partial pressure of oxygen. So here we can calculate it like this. See, P of O2 should be, that is the small p of course, is kh into mole fraction of oxygen. So the mole fraction of oxygen should be the partial pressure of oxygen divided by the Henry's constant. So that is nothing but 0.2 divided by 4.34 into 10 to the power 4. I have calculated it separately and the result is coming out to be as 4.6 into 10 to the power minus 6. Now let us see if we change mole fraction into molarity. So we have calculated, here we can see we have calculated 4.6 into 10 to the power minus 6, that is the mole fraction of oxygen. Now we are calculating, we are changing the mole fraction into molarity. So in that case we can write that moles of water is 1000, because we are calculating in 1 liter, 1000 by 80, which is 55.5 mole. Now of course the number of moles of oxygen is very small compared to number of moles of water, because the amount of oxygen that will be dissolved in water is much less, so the amount of water will be much greater. So if we can write down like this, the number of moles of oxygen plus number of moles of water is almost equal to number of moles of water, because this is negligible quantity. We should be able to write mole fraction of oxygen is equal to number of moles of oxygen divided by number of moles of water. So we should further be able to write mole fraction of oxygen into number of moles of water is equal to number of moles of oxygen. So 4.6 into 10 to the power minus 6 that we have already calculated into 55.5 should be equal to number of moles of oxygen. We have calculated this already and it is coming out to be number of moles of oxygen as 2.55 into 10 to the power minus 4 mole. You should calculate it by yourself. So this is the desired answer that we were searching for.